Word2Vec is an incredibly powerful tool in the field of natural language processing, designed to convert words into continuous vector representations based on their context within a sentence. In this lesson, we're going to dive into the underlying principles of Word2Vec, how it works, and how you can implement it in real-world applications. So far, we've covered the foundational concepts of word embeddings and touched on various techniques like GloVe and BERT, which emphasize just how critical it is to capture relational semantics in language. Now, let's dig deeper into the mechanics of Word2Vec, understanding how it predicts words based on their context. So, imagine this. Word2Vec uses a very clever approach, predicting a word based on the words that surround it. And in doing so, it learns to understand the relationships between words in an incredibly intuitive way. It employs two main models, the continuous bag of words and the skipgram model. The former predicts target words from context words, while the latter does the reverse. It's all about those word associations. Just think about how much this impacts applications like chatbots or search engines, where understanding context is key. So, the next time you're chatting with a bot, just remember, there's a lot happening behind the scenes, with Word2Vec making those conversations feel more human. To understand Word2Vec, let's first grasp the intuition behind it. Imagine you have a set of sentences where context plays a crucial role in determining meaning. Word2Vec operates on this fascinating principle that words appearing in similar contexts will carry similar meanings. This idea is rooted in something called the distributional hypothesis. For instance, think about the words king and queen. They often pop up in similar contexts, right? So, their vector representations, which are just their numerical forms in a mathematical space, will also be located close to one another in what's known as the embedding space. In essence, Word2Vec transforms words into numerical data, which makes it much easier for algorithms to analyze and make predictions. Pretty cool, huh? Now, let's implement the first step by installing the gensim library. This is essential for working with Word2Vec. You can easily do this via the command line using pip. Just type pip install gensim and hit enter. After the installation, we'll import the necessary modules to begin our implementation. This includes gensim as well as the Word2Vec model for creating those amazing word embeddings. Oh, and don't forget to import NumPy for all those numerical operations we might need later. Next, we will define our dataset. Here, we're using a simple list of sentences, and each sentence is represented as a list of words. This structure is super important because the Word2Vec model expects input in this format to truly understand the context in which those words are used. By preparing this dataset, we really set the stage for training our Word2Vec model, which will analyze all the relationships between those words based on their co-occurrences in these sentences. This foundational setup allows us to effectively build semantic representations of words using the skipgram architecture, which is just like a fantastic approach. So let's dive in and see how it all comes together. Next, let's dive into initializing and training our Word2Vec model using the skipgram approach. To kick things off, we'll create an instance of the Word2Vec class from the gensim library. And check this out, we'll pass in our pre-processed sentences as the input data. Now, we need to specify a few parameters that influence how our model trains. First up, the vector size is set to 10. This defines the dimensionality of our word vectors, right? Higher dimensions can capture more nuances, but remember, they also need more data to train effectively. Next, we set the window size to 2, which means for each target word, the model will look at 2 words on either side to truly understand the context. By setting min count to 1, we're ensuring every word in our dataset gets included during training, no matter how often it appears. Now, when we choose SG equals 1, we're enabling the skipgram model, which focuses on predicting context words based on our target word. Finally, we'll set the number of epochs to 100. This tells our model how many times it should iterate over the training dataset. More iterations can lead to more accurate word embeddings, which is exactly what we want. Now that our model is trained, we can access the word embeddings by querying the model with a specific word. For instance, let's retrieve the vector representation of the word cat and print it out. This will let us observe how the model expresses this word in numerical form, capturing its contextual relationships within our dataset. Now, let's dive into how we can implement the functionality to find similar words using our trained Word2Vec model. So, here's the gist. We're going to leverage the most similar method from the Gensum library. This nifty little tool allows us to query the model for the words that are closest in meaning to a specific target word. In our case, that word is cat. By passing cat as the first argument and setting top n equals 3, we instruct the model to return the 3 words that most closely relate to cat based on their vector representations in the embedding space. Now, this operation relies on cosine similarity. Basically, it's a mathematical measure that evaluates the angle between two vectors. Smaller angles indicate a higher degree of similarity. So, the results from this query are stored in the similar words variable, which will then print out to display our output. This technique really showcases the power of Word2Vec in uncovering semantic relationships, and it also validates all our earlier work in creating meaningful word embeddings. By applying this implementation, we can gain valuable insights into how words like cat relate to others within the given context, enriching our understanding of language representation in computational models. Now, let's implement the function to visualize our word embeddings. We begin by defining the visualize words function, which takes our trained Word2Vec model as an argument. Inside the function, we create 2 lists, one for the labels of the words and another for their corresponding embeddings. We iterate through the words in the model's vocabulary, populating these lists with both the words and their vector representations from the model. Next, we employ the TSNE technique to reduce the dimensionality of the word vectors from a high-dimensional space down to 2D. This reduction is crucial for visualization as it translates those complex relationships into a simpler format that we can plot. We create a scatter plot using matplotlib, where each point represents a word's vector position in this 2D space. To enhance interpretability, we annotate each point with its respective word. This helps us see how closely related words cluster together semantically. When we call the visualize words model function, it generates a graphical representation of the word embeddings, providing us insight into the model's understanding of word relationships based on context. And let me tell you, this visualization is a powerful tool for interpreting our embeddings and assessing the performance of the Word2Vec model. The accompanying scatter plot, titled Word2Vec Word Similarity Scores, displays individual words along the x-axis, while their computed similarity scores are plotted on the y-axis. Each point is thoughtfully labeled with a qualitative category, making key patterns immediately visible. For instance, we see apple sitting spectacularly at the top with the highest similarity score of 0.95, labeled as highly similar. Right behind it, we have king at 0.9 and queen at 0.85, both tagged as most similar. This indicates that there's a strong semantic relationship among those terms. Now, if we look at cat at a score of 0.7 and dog at 0.6, they're positioned roughly in the middle, sporting the label moderately similar. This suggests a moderate semantic closeness, a bit expected since both are animals you'd often find in similar contexts. On the lower end of our spectrum, we find car at 0.4 and bike at 0.5, both labeled as less similar, showing that these transportation-related words don't quite align in similarity with our fruit and royalty pairs. So, what can we conclude from all these values and labels? Well, Word2Vec tends to assign higher similarity scores to words that share strong semantic pairs, like apple and orange, or king and queen. It gives moderate scores to words that are related but distinct, like cat and dog, while lower scores are assigned to words that show less contextual overlap, such as car and bike. The numeric range we see, from 0.4 to 0.95, really showcases the model's dynamic ability to rank word relatedness. And those annotated categories, high, most, moderate, and less, are incredibly useful for validating or calibrating applications further down the line, like synonym selection, analogy resolution, or candidate ranking in retrieval tasks. Now, let's implement a simple pre-processing step using the NLTK library for text tokenization. We'll start by importing the necessary modules from NLT. The first thing we need to do is download the tokenizer model, which is essential for breaking down sentences into individual words or tokens. For our example, we'll use the sentence, "The quick brown fox jumps over the lazy dog," and we're going to tokenize that for analysis. Next, we'll lowercase the input text to ensure consistency in our word embeddings. This makes it so much easier to compare words without worrying about case sensitivity. Then, we'll apply the word tokenize function to split the lowercase text into its constituent tokens. This process not only simplifies our data, but also enhances the quality of the embeddings generated by the Word2Vec model by removing irregularities in the input. Next, let's print out the tokenized words so we can visualize the result of our pre-processing step. This foundational procedure is really critical for improving the model's performance, as high-quality, clean data leads to more accurate and meaningful word embeddings. Beyond pre-processing, let's dive into some key parameters like vector size, window size, and the number of training epochs. Finding the optimal values for these can really make a difference in how well your model performs. It's crucial to run multiple experiments and evaluate the quality of your embeddings during this phase. Now, in real-world applications, you'll often be dealing with much larger datasets, and you might want to integrate Word2Vec into a more extensive pipeline. This could mean building custom data loaders, leveraging GPU for quicker training times, and exploring other architectures like GloVe or FastText. They were tailored for certain challenges that Word2Vec doesn't handle as well. As we wrap up this discussion, it's essential to acknowledge that while Word2Vec has impressive strengths, it also has its limitations. For example, Word2Vec looks at words in isolation and doesn't really take into account the nuances of phrases or sentence structure. However, the insights gleaned from Word2Vec laid the groundwork for even more sophisticated models like the transformers architecture, which tackle these limitations by considering the full context in which words appear. In summary, Word2Vec is a transformative approach within the field of natural language processing, enabling us to encode words as vectors based on their contextual relationships. We began by covering the intuition behind Word2Vec and its architectures. Moving forward, we demonstrated how to implement and visualize embeddings, while emphasizing the importance of pre-processing and parameter selection in model training. With this foundation, you are now well-equipped to explore further into the realm of word embeddings and their integral roles in advancing AI and natural language understanding. So, next week, we're going to look at advanced models that have built on the Word2Vec framework, such as BERT and GPT, to see how these innovations are shaping the future of AI interactions.